let's discuss the pace paper. Nancy starts walking from home to Prepalai Academy daily at 5 p.m. and usually reaches Academy by 5:25 p.m. So let us say home is here and Academy is here. This whole thing she takes a time of 25 minutes usually. Let us say this distance is some d. Let's keep it at that for now. One day, Nancy runs into a childhood friend and waits for 25 minutes to talk to her. Okay, so let us say that one day when she is walking, she meets her friend somewhere here. So there she takes 25 minutes to talk to her. She then convinces her friend to come with her to academy. To reach academy by 5:45 p.m., both Nancy and her friend walk with double the usual speed. Okay, so let us first figure out what is Nancy's usual speed. Let us say it is some v. Okay, now we know that speed is distance by time, so she takes 25 minutes. So that is d by 25. Right. So from here to here, Nancy moves with the speed of v, and from here to here with a speed of 2v. While there is 25 minutes, so she meets, there's a 25-minute pause to talk. So 25 minutes is also used up here. The ratio of distance Nancy walked before meeting her friend to distance between Nancy's house and Prepalai Academy. So let us say that from home to where she meets her friend is some x. So obviously the remaining distance is going to be d minus x. Now, Nancy began from home at 5 p.m. and after everything, she reaches academy at 5:45 p.m. while taking a 25-minute break. So total time that she walks when she meets her friend, that time is say some t dash, that is going to be this time interval of 45 minutes minus 25-minute break she took. So she takes a total of 20 minutes to walk to the academy. So out of which she walks the distance x with speed v. So then you can say v is equal to x by some t1. Let us say she walked this in t1 and this in say t2 time. Similarly, now it's also mentioned that she walks double the distance, right? So 2v speed, she'll cover the distance of d minus x in a time of t2. Now from here we can say t1 is x by v and here t2 is d minus x by 2v, but then t1 plus t2 is total time she walks and that is t dash, which is 20 minutes. So we can now say that x by v plus d minus x by 2v equal to 20. But then we have something here. But then here we have v equal to d by 25. Let us substitute for this value of v. So then we will get x by d by 25 plus d minus x by 2d by 25 equal to 20. Now if we calculate, we'll get here 25 by d, let's take common, you'll get here x plus d minus x by 2 into 20. So you take the 25 to the numerator, 25 by d will be common. So we can cancel out 5. We'll get here, if you take LCM, 2x minus x is x plus d by 2. This will give us 4. We'll get this d also this side. Now we have here 5 by 2x plus 5 by 2d equal to 4d. So if you take the d term to the other side, we get here 4d minus 5d by 2, that is 8 minus 5, 3d by 2. So we get 5x equal to 3d or x by d equal to 3 by 5, and that is what the question asks us. See, The question asks us the ratio of distance Nancy walked before meeting her friend to distance between Nancy's house and Trepalai Academy. That is 3 by 5. So you wanted the ratio of x by total distance d. So that's how we do this. It is x by d, 3 by 25. We just expressed velocity as distance by time and use the data given to figure out the new time that she takes to walk from home to academy. Ram whirls a stone of mass 100 gram tied to a massless string of length 1 meter such that the velocity of stone is 4 meter per second square. Okay, so let us say this is one end of the string and he is holding this string of 1 meter such that this end you have a stone and the stone is now going in a circular path like this. Okay, it's not exactly circular. Yeah. Now, he says that this velocity is 4 meter per second while the length of the string is 1 meter and mass is 100 gram. Now, a string, this is a strong, okay. A strong whirlwind causes the stone to accelerate at a rate of 2 meter per second square in its circular path. See, it was moving at a constant speed, but now there is a whirlwind means what? You have like circular winds. So this wind will now make it go very fast like this. Continuously it will go. It's speeding up while being in the circular path. And that acceleration is given as 2 meter per second square. If the string has a breaking strength of 1000 Newton, as in the maximum tension that the string can bear is 1000 Newton, then how long after the whirlwind starts blowing will the string break? Now see here, tension will act in this direction. Tension is what provides the required centripetal force for the body to keep moving in a circular path. Now the value of tension equal to mv square by r. This is centripetal force. So tension in string provides the required centripetal force. Now when this tension becomes 1000 Newton, that is when the string breaks. So mass, when that happens, then the velocity be some v, radius is 1. So we get v square is 1000 by 0.1, which is 10,000. So velocity is 100 meter per second. So you see, initially the string, the stone connected to the string had a velocity of 4 meter per second. But because of such a strong wind blowing, the speed is increased now from 4 meter per second to 100 meter per second. So how much time will that take? So for that, we will just use v equal to u plus at. Final velocity is 100 meter per second. Initially, it was going at 4 meter per second, accelerating at 2 meter per second square. It will take a time of say t. We'll get here 2t is 100 minus 94, 96. T is 96 by 2, 48 seconds. So 48 seconds after the wind starts blowing, the string is going to break because it cannot have a tension of more than 1000 Newton. So if you understand that the centripetal force required for circular motion is provided by the tension in the string, this question is solved. I hope it's clear. What maximum mass m can be hung from the pulley such that small m does not slide? Okay, let us draw the free body diagram for each mass. So here we have small m. So that is 4 kg is already given to us. So we'll have, so you see here the string is going to pull in this direction, tension, but in the opposite direction we'll have friction. On the other hand, we also have mass capital M here. The same string, ideal string, so tension is same throughout the string. and we'll also have its weight acting vertically downward. Now, at the case where m does not slide, so you want the maximum value of this mass m such that the 4 kg block does not slide. So what is the maximum friction possible here? That's what we call limiting friction. So when friction is limiting friction, that value is mu into normal reaction. Mu given here is 0.2, and normal reaction, you will get normal reaction acting vertically upward, weight acting vertically downward. 4 into 10, 40 Newton. So normal reaction is just 40 Newton. We're going to use that here into 40. That gives us 8 Newton. So limiting friction is 8 Newton. Now when the body is in equilibrium, we will get that the tension in the string is exactly equal to limiting friction. So tension is also 8 Newton. Now, when the 4 kg block is at rest, then this capital M mass also has to be at rest because it is connected to the same string. So, if this mass M is at rest, which means the net forces are 0. So, tension balances out the weight. So, we have a tension of 8 Newton here. Mass M, G anyway is 10. So, if M is 0.8 kg, then the friction is limiting friction and 4 kg block does not move. Now, if we give a mass anything more than 0.8 kg, then this 4 kg block will start to slide. So, our answer is 0.8 kg. That is the maximum mass that can be allowed here so that this M remains at rest. If a very heavy mass of 6 kg is hung from the pulley, so the question says that this is 6 kg, then what mass M dash should be kept on M such that M does not slide? Right, let us draw the FBD of each block. So we have 6 kg block here. Obviously its weight acts vertically downward, 6 into 10, 60 Newton. We have corresponding tension acting vertically upward. Now if we draw the block M and M dash, and we have M dash on top, M is given as 2 kg, so let's keep it as 2 kg. Now it's connected to the string, so we'll get a horizontal force of tension. Now the floor between M and the table is rough, so we get a friction here. Now when it is just about to slip, friction is maximum, it is limiting friction. So for M dash, so for M not to slide, the net force is acting on it have to be 0. So that is possible only when tension is equal to limiting friction. And when M does not slide, obviously this 6 kg block will also not slide. So which means the net force on 6 kg block is 0. So in that case, the vertically upward force on 6 kg block will balance the vertically downward force. That makes tension exactly 60 Newton. So we have 60 is limiting friction, which is mu into normal reaction. Now mu value the question states is 0.2. So it is 0.2 into N. So we get N equal to 60 by 0.2. That is 300 Newton. Now we already have, so what is the normal reaction? So we have to get this normal reaction, right? So you see it is supporting two blocks of mass 2 kg and M dash. So we will get that normal reaction is exactly equal to 2 plus M dash into G. So 300 equal to 2 plus M dash into 10. So 2 plus M dash is 30. That makes M dash 28 kg. So only if you keep such a heavy mass of 28 kg on top of 2 kg block will we be able to prevent this M from sliding. Okay, that's how we solve this problem. A satellite of mass M orbits around Uranus in an orbit of average radius r. Okay, you've been given mass M of the satellite and the radius r of the orbit, and time period is some t hours. Now the satellite reconfigures itself such that the size shrinks to half while the overall mass remains unchanged. So the mass is now same m. In the process, it also adjusts its course and doubles its original speed. What is the new time period of satellite? It is say some t dash. Now, for a satellite orbiting in an orbit with some velocity v, so it's in a circular path, right? So it will have an orbital velocity of some VO. Now, for any body to move in a circular path, there has to be some centripetal force. And in the context of satellites, that centripetal force is supplied by the gravitational attraction. So in this case, the average radius is also given as r. So we have g m. Let us say satellite has a mass m, and Uranus has a mass of say m dash. So then it will be g m dash by r square. This is centripetal force, and centripetal force is given as mass of the orbiting body, orbital velocity square by r, mv square by r. So here we get m cancelling out, and we get v naught square equal to g m dash by r. So v naught is g m dash by r under root. Now here the new orbital velocity is going to be double the old velocity. That is what he says. We also need to find the time period t. Now velocity is what? Distance by time. Satellite takes one time period to go through the whole circumference of the orbit, the length of the orbit. Nothing but circumference. It is going to be 2 pi r by t. So we have a time period t of 2 pi r by v naught. Here it is 2 v naught. That is going to be new time period 2 pi r dash by t dash, where r dash is the new radius. Now only if we find out this value of r dash can we get the new time period. Now how to get the radius of the new path? Again, we are going to use the concept of gravitational attraction being the centripetal force required. So we are going to get g m dash by new radius square is going to be m. New velocity is double the old velocity. So this whole thing squared by r dash. So one term can get cancelled here. We will get this m also cancelling out. We will get g m dash by r dash is 4 v naught square. But we already have v naught square here. We will substitute for that. We will get gm dash by r dash is 4. V naught square is gm dash by r. So we are left with 1 by r dash equal to g by 4 by r. This anyway gets cancelled. So the new radius is going to be 1/4 the old radius. Let's make use of this. So we get t dash is 2 pi, r dash is going to be r by 4 by 2 v naught, right? So this 2 gets cancelled, or we can keep it as it is, don't cancel the 2. We are left with 2 pi r by 8 v naught. This is t dash, but you see 2 pi r by v naught is already give t. So we get t dash is 1 by 8 of 2 pi r by v naught. So our new time period is 1/8 of the old time period. Okay. All we used is the fact that gravitational force of attraction provides the needed centripetal force for the satellite to orbit in the circular path. Also, please notice here that the fact that the size of the satellite shape changes does not really affect the problem at all. Irrespective of how big or small the satellite is, it is the mass of satellite that matters, which by the way also gets cancelled. So it is the velocity of the orbit, velocity of the satellite in the orbit that actually accounts for the time period. That's how we solve this problem. A man can jump to a maximum height of 8 feet while on Earth. Okay, how high can this man jump on Jupiter, whose mass is 319 times mass of Earth? Size is 11 times. So let us say Earth has a mass m and a radius r. Then Jupiter has a mass of 319 times m and radius of 11 times r. Okay. Now, he can jump to a height of 8 feet on Earth. How high can he jump on Jupiter? Now, how high a person jumps depends on the value of acceleration due to gravity. Now, we know that on the surface of Earth, the gravitational force of attraction is equal to the body's weight. This m gets cancelled. We get G is gm by r square. Now, how is height related to G? Whenever a body is thrown up, so with the person, when a person jumps from the ground, he gives himself an upward velocity of u. And at the maximum height, he'll come to rest momentarily. While G always acts vertically downward. So V square minus U square is 2AS, we know. This V is going to become 0 at the highest point, and the gravity acts in a direction opposite of initial velocity, hence the minus G, and this S is the maximum height he can jump to. So we get H is U square by 2G. So how high he can jump, the U square he can produce with his legs is a constant, same person, right? So the higher the value of G, the lower the height he can jump. So you see here H is directly proportional to inversely proportional to G. We have to come to this conclusion. Now on Earth we already know G is gm by r square. Now how about on Jupiter? On Jupiter it is going to be G dash, say G m dash is mass of Jupiter by r dash is radius of Jupiter whole square. That gives us G dash is equal to G 319 m by r is 11 m whole square. That is 319 by 121 gm by r square. But then we already see that gm by r square is G. So this is 319 by 121 into G. So let's make use of this. So we have now H by H dash is equal to G dash by G. From here we can say G dash by G is 319 by 121. So we get H by H dash is 319 by 121. But we want H dash, that is H into 121 by 319. Now that H is 8 feet. So 121 by 319 into 8, right? Yes. So now let us calculate this value. 121 into 8. This will be 968 divided by 319. It comes out to be around 3.03. So we can approximate it as 3 feet, which means he can jump as high as 3 feet on Jupiter if he can jump 8 feet on Earth. When we know that Jupiter is 319 times heavier than Earth and 11 times larger than Earth. Okay, that is the answer. The velocity of each block as seen by Alex standing on the ground is shown. Okay, choose the incorrect option. So which of the following is incorrect? Now here we have to decide the direction of kinetic friction between each of the blocks. Okay, now kinetic friction by definition acts in such a way as to oppose the relative motion. So if we want to figure out the kinetic friction on B due to A, so A is causing the friction on B. So let's get the velocity of B as seen by A, which is velocity of B minus velocity of A. Now let us take this side as being positive. Now B has a velocity in the opposite direction, hence it is minus 8 minus velocity of A is 10. which is minus 18 meter per second. Now what we have to look at is the sign. The negative sign shows that as seen by A, B has a tendency to move in the negative direction. Okay, that is what you mean by velocity of B as seen by A. So to prevent that, we'll get friction between A and B like this. So consequently, you can also say consequently that VAB is going to be minus of VBA, which is 80 meter per second. So as observed by B, A has a tendency to move to the right side. So let us also draw A here. So A has tendency to move like this. So to prevent that, B will exert friction on A in the opposite direction. That's how we get the frictions between A and B. Similarly, let's get the direction of friction between B and C. What is the velocity of C as seen by B? That is velocity of C minus velocity of B. Now C moves to the right while B moves to the left, hence the minus sign. So it is 12 meter per second. So let us also draw C here itself. So here, as seen by B, C is trying to move this side. The positive sign shows right side. So to prevent that, friction on C because of B will be in the opposite direction, left side. Similarly, velocity of B as seen by C is minus of VCB, which is minus 12 meter per second. So when C observes B, B appears to move in the opposite direction. So when C watches B, B is moving this side. So to prevent that motion, it will exert friction on B in the opposite direction. So now we have all the directions of friction. Let us see which options are right and wrong. Now, kinetic friction on C due to B is this one. It is to the left, which is correct. Next, kinetic friction on A due to B. So on A due to B, it is this. It is also to the left. So this statement is also correct. Kinetic friction on B due to A and C. So on B due to A is to the right, due to C is also to the right, is to the right. So that also is correct. So obviously on B due to A to the right, C to the left, this is wrong. It is also to the right. So D is our answer. D is the only incorrect option here. Okay. We decide the direction of friction by observing the tendency for motion of one body as seen by the other. Basil stands at one end of a long boat of length 5 meter, which is floating with a uniform velocity on water surface. So let the boat be something like this. It's floating with uniform velocity of some v and the length of the boat is 5 meter, right? Basil now, so let us say Basil is at this end. Now he starts walking with a velocity of 0.5 meter per second with respect to the boat. If the boat comes to rest when Basil starts walking, what is the initial velocity of the boat? He's asking us this value. Basil and boat have same mass, so if this guy has mass m, boat also has same mass m. Assume water surface is perfectly smooth. Now, what happens whenever we walk? When we walk, we push the ground backwards. So, when Basil walks from here to here, he is pushing the boat backward in the opposite direction. But then the boat is moving forward, which means effectively since he is pushing the boat backward, it nullifies this velocity and the boat comes to rest. That's what he's saying. If boat comes to rest when Basil starts walking. So he's telling us that because he pushes the boat backward, now the boat comes to rest. Then what is V? Now, here what we have been given is the velocity. So this is the velocity of the man with respect to boat. That is 0.5 meter per second. This is velocity of man minus velocity of boat, which is 0.5. But in the end, the boat comes to rest, which means this value becomes 0, which means velocity of man is also 0.5 meter per second. Now here, before he starts walking, that is initially man and the boat. So man and the boat together are moving with this velocity v. But finally, the man is walking with speed vm and the boat comes to rest. So velocity is 0, momentum is 0. Now you see here, if you take this whole thing as a system, there is no external force. Even the water surface is said to be smooth, so there is no friction there. The only forces acting here are on the man, there is friction forward, and on the boat there is friction backward. Okay, but on the system as a whole, the net force is 0. Okay, so we can conserve momentum for the whole system. See, we are not conserving momentum for the man or the boat separately. We are conserving momentum for this whole system. Whole system initially moving together with same velocity v. So momentum initially is total mass of man and boat into v. Finally, the boat comes to rest, but the man has this velocity. Now, since the net external force is 0, change in momentum is 0. That is initial momentum equal to final momentum. Initial momentum is 2m into v. Final momentum is just m into vm is 0.5. This thing gets cancelled. We are left with v equal to 0.5 by 2. V is 0.25 meter per second, which means initially the boat was moving with a velocity of 0.25 meter per second. So when this man starts walking at 0.5 meter per second with respect to the boat now comes to rest. Okay, the boat comes to rest because the man is pushing the boat this way because of this friction. This friction will now bring this boat to rest. Which is the following is incorrect. Kepler's laws are empirical. Now what do you mean by empirical? Empirical means those laws which we come to the conclusion from observing nature. So there are theoretical and there are empirical. Theoretical means you do some theoretical calculations and you get the final result. But empirical means you're observing what's happening and you're coming to conclusion. So Kepler proposed his 3 laws from observing how planets are moving, how stars are moving. So Kepler's laws are empirical. They are not theoretical. Okay. Now Kepler's first law says that the planet orbits in elliptical path with sun at such that the sun is in one of the 2 foci, which is correct. This is Kepler's first law, which we also call law of orbits. Next, planet moves faster when it is closer to the sun and slower when it is further from the sun. Now this is based on Kepler's second law. How do you figure it out? So we know that the planet has an elliptical orbit like this. Now ellipse has 2 foci. One focus is somewhere here, S1. Other focus is somewhere here, S2. So let us call it F1 and F2. Now let us say the sun is at F1. Okay. So the planet will move such that the aerial velocity remains constant. This value is constant. Now what do you mean by aerial velocity? The area covered per unit time. So you see, if the planet say starts from here A and it goes to B in some time t, the aerial velocity is this area. So this area, this shaded area, this area by t, that is aerial velocity. Similarly, so the line joining so Kepler's second law states that the line joining the planet to the sun covers equal area in equal time. The aerial velocity remains constant. Similarly, when the planet is now say on the other side, so say it is somewhere here at P and now it comes to say Q in the same time t, in the same time interval t, then I'm going to remove this focus for now. If we join these lines, Then what is this area? This green shaded region is that area. So what Kepler says is this area and this area are the same because the time taken to go from A to B and from P to Q is same. So now that we understand Kepler's second law, let us see how the planet moves. If these areas are same, then see this distance is small, but if total area has to be large, it obviously has to cover larger length in the same time t, and because this length is long, it needs to cover only a short distance in the same time t. So you see, in this situation, planet is faster. That is, planet has higher velocity or it is faster. Whereas in this case, planet is slower. So clearly you can see here that when the planet is closer to the sun, it is faster. But when it is at a further distance from sun, it is slower. Then which among C and D will be true? Faster when it is closer to the sun, slower when this is true. Obviously, then this is incorrect. So D is the incorrect option, which is our answer. Netra is driving on a highway and there is a truck driving in front of her. She wants to overtake this truck, but then she sees another car coming in the opposite direction in the other lane. Top view is given. So with what minimum acceleration should Netra drive from this moment to safely overtake the truck? So we have been given the velocities of the truck, of Netra and the car coming in the opposite direction. And if you observe the units, it is kilometer per hour. So let us convert it into meter per second. And to convert, we multiply with 5 by 18. So here we are going to get 36 into 5 by 18. That is 10 meter per second. Here we are going to get 72 into 5 by 18. This is 4 times. So this is going to be now 20 meter per second. And here we have 54. So 54 into 5 by 18. This is thrice. This is going to be now 15 meter per second. Now you see the truck, the car and Netra, all three are moving. So it's kind of hard to imagine what's happening. So now what we'll do, we'll put the truck at rest. Not exactly at rest, we are now going to observe how the car is moving and how Netra is moving as seen by the truck. So what we are doing is we are trying to figure out the relative velocity. So what is the velocity of Netra as seen by truck? That is velocity of Netra minus velocity of truck. Netra is moving at 20 meter per second and truck at 10 meter per second. So it is 10 meter per second. So relative velocity of Netra with respect to truck is in this direction of 10 meter per second. Similarly, what is the velocity of the car as seen by the truck? If you see here, the car is coming in a direction opposite to that of truck. So we'll put a minus sign to denote that. So velocity of car minus velocity of truck. Because car is coming in the opposite direction, we put a minus there. Minus velocity of truck is 20. No, it's 10. That is minus 25 meter per second. The minus shows that as seen by the truck, car has a velocity towards the truck as it is in this direction. So that value is what we figured out. Velocity of car with respect to truck is 25 meter per second. Now, Netra has to overtake the truck without crashing into the car. So you see Netra is here now. Netra is safe if she can drive and come to this position before the car reaches. Okay, since the length of the car is not given, let us think of it as point and calculate how much time car will take to go from this level to this level. Now this length is 100 meters already given to us. It's 100 is already given to us, right? So then So time taken by car to reach truck, that is equal to the distance between the car and the truck by the velocity of car with respect to truck. So it is 100 by 25 in magnitude, not direction. Okay. So 4 seconds. So you see here, the car just takes 4 seconds to come here. So within that 4 seconds, Netra must cover and reach here. So you see, Netra must now come to this position. So I'm going to show her position in a dotted line. So you see, Netra was initially here, right? Netra must now cover this distance of 50 meter, and then she must cover the length of truck 15 meter and the length of her own car 5 meter. Only then, see, the starting of Netra's car is here, and that reaches here now. So total distance is this distance. So now we can conclude then that distance Netra must cover, that is the length of her so here if you see the 50-meter separation between the truck and her car, the length of truck 15 meter plus length of her own car, that is 50 plus 20, 70 meter. Now Netra has to cover 70 meter within 4 seconds for her to be safe. Let us say she covers it in just 4 seconds. So we want to get the minimum acceleration required, right? So let Netra take 4 seconds. Then we will get the minimum acceleration Netra needs to apply to be safe. Now we already know that distance S is equal to ut plus half a t square. We got that distance of 70 meter. Netra must cover this distance with initial velocity. Again, we are observing everything with respect to the truck. So we will take the velocity of Netra with respect to truck only. That is u, time we just got 4 plus half acceleration and 4 square. So we have now 70 minus 40, 30 is equal to half a into 16. So we have 30 equal to 8a. A is 15 by 4. That is 3.75 meter per second square. So if Netra gives this much, this is actually the minimum acceleration. So if Netra goes faster than this acceleration, then no problem. She'll comfortably overtake the truck and she'll be safe. But if she goes with acceleration of less than 3.75 meter per second square, then she is probably going to crash. This is the minimum acceleration required. So if that is the case, it's better she does not try to overtake the truck. So she'll be safe. Okay, that's how we solve this problem using the concept of relative velocity. Consider lift accelerating as shown in the figure. If the 10 kg block is at rest inside the lift, then what is the deformation in the spring if it has a stiffness of 1000 Newton per meter, right? Now, because the lift is going up, this block also has to go up. So you are standing outside and looking at the lift, then obviously the lift is going up, the block also is going up. But if you imagine yourself standing inside the lift, you are going up with the lift, but the block will appear to be at rest with respect to you. So here this is called the ground frame. And this is the reference frame of lift. So in the reference frame of lift, see what you will get. You have a block. The mass of block is 10 kg. Now, whenever you take a reference frame that is accelerating, We apply Newton's laws of motion only after putting something called the pseudo force. And pseudo force has direction always opposite to direction of reference frame. So in our case, the lift is accelerating upward. Pseudo force on this block will act downward, and it has a magnitude of mass into the acceleration of 20, that is 200 Newton. Now its own weight will act 10 into 10, 100 Newton. Now you see, because of this force, the spring is now going to get compressed. Now when the spring gets compressed, it will exert an upward spring force. But you see, this 10 kg block is now at rest inside the lift, which means the net upward force is equal to the net downward force. So K value is 1000 equal to 300. So we are getting X is equal to 3 by 10, which is 0.3 meter or 30 centimeter. And clearly, because it is upward, it is compression. See, this is the natural length of spring. When you push it down, the spring will push you upward. That happens only when the spring is being compressed. That is what is happening in this case. But if you now pull a string upward, this string will pull you back downward. So always remember, the spring tries to go back to its original shape. So it will apply a force so as to bring itself back to its original shape. So this question is based on the concept of pseudo force. This is a pseudo force. So the answer is 30 centimeter compression. When body is at a height of h from surface of planet, its acceleration due to gravity is half the value on surface of planet. So let us maybe draw a planet here. This planet has a mass m and radius r, or maybe we can do something like this. We'll take a small planet of mass m and radius r. So on the surface of planet, the value of acceleration due to gravity is, say, some g. Now, at a height of h, the value is g by 2, half the value of value on surface. Now he's saying that if mass of planet is doubled and radius of planet is halved, so you're having a smaller planet of half the radius while the mass is doubled. So now we have 2m and r by 2. So doubled and halved. At what altitude will acceleration due to gravity be 1/4 the value on the surface of original planet? So now we want to find out this altitude h dash, such that the g here is g by 4. It is 1/4 of this original value. So you have to get this h dash. That is what the question asks us. Now, how do we figure out the value of acceleration due to gravity? Now we know the body's weight is nothing but the gravitational attraction that the body experiences. So on surface of Earth, Gmm by r square, where m is the mass of the body, is equal to mg. So we get g is gm by r square. Now, at a height of h from Earth's surface, then what is the force of gravitational attraction? Is going to be gmm by r plus h whole square from Newton's gravitational law. See, the distance from this point to center of planet, so it's r plus h. Okay, that value is now going to be m. Now at that altitude, the value is g by 2. So directly I am substituting it. Okay, this m anyway gets cancelled. So here we get gm by r plus h whole square is half of g. But then g we just found out is gm by r square. So let's substitute that. This is half of gm by r square. This gm gets cancelled. We are left with r plus h whole square is 2r square. So we can rearrange these terms. So r plus h by r can be written as r by r, which is 1, plus h by r. You take the root. So we are left with h by r is root 2 minus 1, or h is r into root 2 minus 1. So we now have figured out the value of h in terms of r, or let's also say r in terms of h by root 2 minus 1. Leave it at that. Now we need to find h dash in terms of h. That's what the options are all about. Now in this planet, on this planet at height h dash from surface, what is the force of gravitational attraction? It is going to be g. Mass of planet is doubled. Mass of body anyway is same. By now the distance from the center to this point is of course height h dash plus the radius, which is now half the original value. So it is going to be r by 2 plus h dash. This is equal to m. Now the question also states that at this point the value of acceleration due to gravity is 1/4 original value. So we will substitute that new value here. M anyway gets cancelled. We are left with 2gm by r by 2 plus h dash equal to 1/4. Let's substitute for g here. We get gm by r square. The gm can get cancelled. So if we cross multiply, we get r by 2 plus h dash. There's a square term here because of gravitational law. This is going to be 4 2s are 8 r square. So if we take square root on both sides, we get r by 2 plus h dash is root 8 is 2 root 2 and r will come here. We get h dash is 2 root 2 minus 1 by 2 into r. So we get h dash, take LCM, this is going to be 2 into 2, 4 root 2 minus 1 by 2 into r. But we just found out the value of r in terms of h. Let us substitute that. We get 4 root 2 minus 1 by 2 into r is h by root 2 minus 1. So let us now rationalize the irrational term. So for that, let's multiply with root 2 plus 1 by 2 root 2 minus 1 root 2 plus 1, and of course we have h here. So the denominator now becomes root 2 square is 2 minus 1 is 1. So we just get 4 root 2 minus 1 into root 2 plus 1 by 2 into h. Now we have to expand these two brackets. So 4 root 2 into 2, 4 root 2 into root 2 is 4 into 2, 8. 4 root 2 into 1, 4 root 2. Minus 1 into root 2, minus root 2. Minus 1 plus 1, minus 1. Whole thing by 2 into h. So if we calculate this, that becomes 8 minus 1, 7 plus 3 root 2 by 2 into h. And that is our answer. All we applied here was the definition of weight. Weight is nothing but the gravitational attraction. From there we figured out the acceleration due to gravity at different locations. So 7 plus 3 root 2 by 2 into h. Okay. A new delivery service delivers daily essentials using drones within 5 minutes. Sadhana orders eggs. Now the delivery drone has an unexpected malfunction and drops the eggs near Sadhana's doorstep before it comes to rest, which means it drops the eggs while it's already moving. With what speed should Sadhana run to catch the eggs just in time? Okay, so you see the eggs are dropped here while the drone is flying like this. So if you can imagine how the eggs would move something like this. Okay, now we have to figure out where it will land and how much time it will land in. then we can know how much time, how much distance this would be between Sadhana and the point where the eggs would hit the ground, and then we can calculate the speed. Now, how to find out this distance x at which the eggs will fall and how much time it takes. So here, if you see, the velocity is only horizontal. There is no vertical component of velocity. So it has to now fall through a height of h. So h is ut plus half a t square vertical direction. Now in the vertical direction there is no velocity, only horizontal velocity is there. Okay, so it has to fall through a height of h. Half acceleration is 10 t square, so t square is 5 into 2, 10 by 10, 1, which means t equal to 1 second. So within 1 second the eggs will now fall to the ground. Now what is x? See, there's only acceleration downward g. There is no acceleration horizontally. So you can now say that x will be equal to that u into t. This is in the horizontal direction. So that x is going to be, u is 8 and time t is 1 second. So x is 8 meter, which means distance Sadhana must run is 20 minus 8, which is 12 meter, and time Sadhana has is just 1 second. So you see here, while the eggs take 1 second time to fall here, Sadhana must reach at this point in that 1 second. So for that, the velocity of Sadhana is supposed to be how much distance she must cover and in how much time she will cover that distance. So it has to be 12 meter per second. If she runs slower than 12 meter per second, she will not reach this point before the eggs fall. So eggs will fall and break. If she runs faster, she will cross this point. She will be here when the eggs fall here. But if she runs exactly at this speed, she will be at the exact location ready to catch the eggs. She will be just in time to catch the eggs. So that's how we solve this problem. Two friends, Raju and Sham, are playing hide and seek. Okay, this is R. Raju is hiding behind a wall, but Sham sees him and starts chasing him. In how much time will Sham catch Raju? So in the figure, we know the separation of Sham and Raju and their respective speeds. So as soon as Sham sees Raju, he's going to start running. He's going to start running and chase Raju. So let us say that they both will meet when they reach, say, this point. So that distance between Raju and this point of meeting is, say, some x, which means if they are both meeting in this at this point in the same time t, then in that time t, Raju has covered distance x while Sham has covered a distance of 10 plus x. Now see, we know that for Sham, speed is equal to distance 10 plus x by time t. Whereas for Raju, his speed at 10 meter per second, he'll cover distance x in time t. So we get t here 10 plus x by 12, and here the same t is x by 10. So we can equate them now. 10 plus x by 12 equal to x by 10. So here this is going to cancel 5 times, 6 times. So we get here 5 into 10 plus x equal to 6x. So 50 plus 5x is 6x, or we get x equal to 50 meter. Now we want the time t. Time t is 50 by 10, 5 seconds. So in just 5 seconds, Sham will catch Raju as soon as he sees Raju. That's how we solve this problem. I hope it's clear. Athletes are practicing shuttle run. 10 small cones are placed at a separation of 5 meters from each other. The first one is placed 5 meters from the starting line, and the last one 5 meters before the finish line. So, two friends, Tom and Ben, start at the same time but in opposite directions. If Tom has average speed of 5 meters per second and Ben has average speed of 10 meters per second, then which cones, between which cones do Ben and Tom meet? Separation is 5. So what the question says is between start and cone A, between A and B, C and D, between any two cones, it is 5 meter. Now, what is shuttle run? It's for Tom, it will look like this. He'll run from starting line to A, come back, run back to starting line. He'll run to B, come back to starting line, run to C, come back to starting line, run to D, come back to starting line. So on, he will go till the finish. Same way, Ben also will go, but in the opposite direction. So he'll go further every time. So like this, he'll keep on doing. They're running the same line, but they'll touch the first cone, come back, then next cone, come back like that. So Tom is going to start that in this direction, and Ben opposite like this. Then between which cones will they meet? Now we already know separation of each cone is 5 meter. Then let us see how much time Tom will take to go from first cone to the next one. So for Tom, his speed is 5 meter per second. Separation between the cones is 5 meter. He'll take a time of t1, which means he takes t1 equal to 1 second to go from one cone to the next cone. Then Ben, his speed is 10 meter per second. Separation is 5 meter. He'll take say a time of t2. Then t2 is 5 by 10.5 seconds. So now we know how much time Tom and Ben will take. Tom takes 1 second to go from start line to one cone or from one cone to the next. Whereas Ben will do the same in just half a second. So now let us see where they will be at different times. So let us start with Tom. So here, please observe carefully. We're drawing the path that Tom will take. Tom is here initially. He'll be here in 1 second and he'll come back to start line 2 seconds. He's in at 2 seconds, he's at the start line. Then 3 seconds from A to B, 4 seconds. B back to A, 5 seconds. Then A to starting line, 6 seconds. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so almost the center we have reached. So I'm just showing it here. He's running now towards E, but this is at T equal to 24 seconds. Now we know how Tom is running. So from time instance starting point to 24 seconds, he'll be at D and he'll be running towards E. So let's stop here. Now let us look at Ben. Now we know Ben only takes half a second. So to go from the start line to the cone J, he'll take half second. To return another half second. So 1 second he's back at the start line. Then again half. So one, one and a half, two, two and a half. Okay, sorry. Two and a half, three. Again at 3 seconds he's back at the start line. Three and a half, four, four and a half, five, five and a half, six, six and a half, seven, seven and a half, eight, eight and a half, nine, nine and a half, 10. So in 10 seconds, he's now back at the start line. So again, 10 and a half, 11, 11 and a half, 12, 12 and a half, 13, 13 and a half, 14, 14 and a half, 15, 15 and a half, 16, 16 and a half, 17, 17 and a half, 18. Next, 18 and a half, 19, 19 and a half, 20, 20 and a half, 21, 21 and a half, 22, 22 and a half, 23, 23 and a half, 24. See, he is now at E at 24. He's running towards D. This is T equal to 24 seconds. So, now I'm going to use a different color to differentiate. From 24 to 25, he is going to come from here to here. T equal to 25. No, this is 24 and a half. This is 24.5 seconds. Whereas our Tom is going to go from D to E in T equal to 25 seconds. So do you see that they're going to meet here only? Okay. So while Ben is running from here to here, Tom is running from D to E, while Ben is running from E to D. So they both meet between cones D and E. That's how we solve this problem.